enough.
So what's the force? Would you know if a force is applied to you?
Something that's acting upon something?
Okay. It is the action and not the something. Because you know, there's objects involved in the force, and then there's the actual interaction.
Would it be the transfer of energy?
It depends on what you mean by transfer of energy.
I mean, like, if I push Ethan, that's a force, right? But I'm also transferring energy.
Yeah, see, there's, when you say transfer of energy, there are some forces that will transfer energy from one object to another, and there's some forces that will transform energy from one type to another.
I got you.
So that was the distinction I was putting in there. But you did hit upon a key point in that when you said you pushed. So pushed or
Pull.
yeah, that's probably the best working definition of a force. There's a formal definition and an influence that might cause acceleration, which I find to be an incredibly unhelpful definition. So the push or pull works. So what we're about to proceed on, this is material that would be on test, the second test, is we're heading towards a technique for solving problems, which I refer to as the facades method. We'll spend today working on the first part. So F for force diagram. Now textbooks and the Sassen refer to it as a free body diagram. I'll get into the distinction between the two. A, acceleration, and comma, direction of. So so in a problem, first you'll do a force diagram, then you'll figure out the direction of acceleration. Once you have the direction of acceleration and you have the forces listed, you then determine or define your coordinate axes. We're trying to keep you on your toes.
Yeah, because you're not in 3:30?
I think Mondays and Wednesdays were officially in here, but I generally go down there on Mondays. Wednesdays, Tuesday, Thursdays were across the hall, and Wednesdays I think the Sassen gets there first, and so last Wednesday we were in there.
Oh, okay.
It basically, I've marked territory in all three rooms, and so
You're being greedy.
yeah. Do you want to be filmed?
That's fine.
Okay.
Am I interrupting? Did you need to
Oh, of course you're interrupting.
Will it be on that? Did you finish that one? Or is it okay?
No, that's probably as good a time as any. I'll just repeat myself. Here's Mike Jones. I knew he was coming, but then forgot. So.
Yeah. Well, yeah, hi, right. I'm Mike. Some of you already know me. I'm a tutor with the Learning Center. I work in our STEM drop-in lab. Are y'all familiar with the free one-on-one tutoring that we have available? Do y'all know about the drop-in lab? Yes? Yes? Okay. So this will be really easy. Basics 101 is you make an appointment to navigate. It covers a lot of different topics. We do have physics people that you can meet with both in person and virtually, depending on what you need, and covers all kinds of different topics. So feel free to look into making appointments with them. It's all free. Just to reiterate. And then I work over in the drop-in lab. Right now it's 10 to 6 Monday through Thursday, 8 to 3 on Friday, and I'll resend you time information.
Okay.
If you want to just throw it on whiteboard so they don't have to remember that necessarily. It is over in Strickland on the second floor, near the little ATM with the Bitcoin thing on it, which is always a little laugh. Yeah, it's something like.
I'm currently watching the documentary VidCon.
Oh.
It just makes me distrust it even more.
Oh yeah. So it's drop in. If you don't know how that works, you just come in with your student ID number, put it in, sit down. If you need help immediately, let myself or any of the other tutors in there know. If not, a lot of people like to just come in with, say a master set and just start working on it. And whenever you got a question, say, hey, you get some help. Talk, 10, 15 minutes, and then let you try it, see if you've kind of understood now what you were missing. And a lot of students, they'll come in for like 2 or 3 hours to just, have at least like a security blanket there, just in case, because there's probably gonna be questions. You don't make it easy on them.
This group will understand everything the first time.
So that's pretty much the basics. I have little handouts that I'll leave. Does anybody have any questions about it at all? Nope. Fantastic.
I would say, I probably mentioned this before, he was one of my students years ago. 10 years ago? Longer?
It is, yeah. That was 2013, so.
Yeah, more than 10 years ago. So he took 251 or 252 from me, but he's been tutoring here for
5 years now.
It felt like longer.
Yeah.
For 5 years. He understands a lot of the questions you'd be looking at and going, wait, this doesn't make any sense. He knows how to translate.
Yep.
And the others are newer, so I don't know them. I hear their names and then promptly forget.
I know Avery does some. He's doing mostly chemistry.
Okay.
He gets booked up with the chemistry. So it's more or less kind of just be still.
Okay.
With Stuart gone and everything. Rest in peace. He didn't die.
Yeah, no, I think I would refer.
Yeah.
Stuart was another former student who did tutoring for a brief stint.
Yeah. I'm gonna later a little bit. So this just goes over how to make appointments, just in case you don't know, and then information about the different tutoring services. I'll let y'all get back to it.
And presumably now that you're on the video, all the international fans will be contacting you as well.
Yes, of course. Yeah. Contact my agent first.
Okay. Yeah. So for the international fans, contact his agent.
All right. Bye.
All right. As we last left off. Coordinate axes, you're going to define the I-hat, J-hat direction. Now, always picking I-hat horizontal and J-hat vertical, you will find that that is not necessarily the simplest way of doing it. Matter of fact, I did a video where I solved it. I solved a box on ramp problem with the coordinate system in the simplest way, and then with the horizontal vertical. And I think that if you stuck with horizontal vertical, it's about 4 times the math. So we'll get into that. D is for decomposing the vectors. The equivalent with scalars is if you have the number 3, you go, oh, that's 1 plus 2. It's basically finding what vectors can I add together to create the vector in the diagram. E is for equations of motion. And this is all based on Newton's second law, F equals ma. This is not based on the formulas from chapters 2 and 3. Matter of fact, the equations of motion might still apply even if it's not moving. S, substitution. And the second S, to solve. Typically in a problem, you're solving for acceleration. So those are the steps that we will work through. However, today we will concentrate on F. Questions to hear? All right, force diagrams. With a force diagram, we're basically analyzing the forces that are involved in a problem. We are drawing them on the diagram. And so I'm going to start out with a list of all the forces that we need at this point. Another mnemonic, FTOM. This F stands for friction. T for tension, O for other, because sometimes we don't know what kind of force it is, and also I needed a vowel. N for normal, and G for gravitational. There'll be other forces as we go. The elastic force or spring force is one that would definitely hit, and potentially a buoyant force, but that's several chapters down the road. Gravitational, there are two types. There is weight, and then there's the generalized, I'll just write generalized. And yes, I realize one's a noun and one's an adjective. We'll go with it. So if I'm talking about a small object near a huge object, such as a person or an elephant near a planet, then I'd be talking about weight. If I'm talking about the relationship between Earth and Sun, well, weight doesn't really work very well there, so we use a generalized gravitational force. That's chapter, I think, 6. The symbols that I use for friction, I use what I call a Baroque F, but a little bit of a flair to it. That's what I use for friction. For tension, I use a capital F with a subscript T. I used to use capital T, but there will be a point later on in which basically we would have tension and something called period, which period is used as a capital T. And so instead of using capital T for tension now and then later going, all right, we're not going to do that anymore. We're just starting with F sub T for tension to start with. The symbol I use for normal force is a capital Y, because we don't use capital Y for anything else in this course, and my high school physics textbook used a capital Y and it's stuck. For weight, I use a lowercase w. I indicate my lowercase w's by the little bit of extra flair on the end, the flange, the serif. And then for generalized, F with the subscript G. Other is problem specific. If you don't care, or from a physics point of view, try that one again. If you don't know, or from a physics point of view, you don't care what is the source of the force, that's when the other pops in. So it is problem specific. So a 3 Newton force is pushing on a 5 kilogram box. What's causing that 3 Newton force? I don't know. That's an example of other. Of these, well, other we don't know, but this is the one between the friction, tension, and normal. Gravitational force is the one that does not require contact. No contact required. The others require contact. Questions here? All right, friction. So the requirements. Friction requires contact and desired relative motion. This is friction. Desired relative motion. In other words, if the surface were frictionless, would the objects move relative to each other? Tension. The requirement is a tight or taut rope, chain, string. It's a pulling force. Other is problem specific. Normal force requires contact. And the gravitational force requires two masses. If we're talking specifically about weight, yeah, it requires two masses, but one of the masses, one mass, huge, and the other relatively small. And near each other. Dramatic pause for people who need me to read my handwriting.
Can you go over the white one?
All right, so generalized gravitational force just need two masses. There's a gravitational force between me and you, between you and the desk, between you and the light fixture, etc. These are incredibly small forces. Weight, you need a huge mass such as a planet or a moon, and something small relative to that is near the surface. So I am near the surface of the Earth is huge, I am small, there's a weight involved. The Earth is pulling down on me. I'm pulling up on the Earth as well. So one mass huge, such as a planet or moon. The other relatively small, such as a building or an elephant. And they are near each other. Did that answer your question? All right. Other questions right now? All right. So the forces. Okay, first off, forces come in pairs. Just write that up in bold print. Forces come in pairs. Each force in that pair acts on a different object opposite directions, but same type and magnitude. So I said before that the Earth pulls down on me with my weight. I pull up on the Earth. I weigh about 215 pounds. So the Earth pulls on me with 215 pounds. I pull up on the Earth with 215 pounds. If I went up on the desk and I stepped off and I fell, I'm falling because the Earth is pulling down on me, but I'm pulling up on the Earth. And so the Earth does move up towards me, and I've worked out the math there, and it moves up about the diameter of the nucleus of an atom. So nothing noticeable. Again, the opposite directions. The Earth's pulling down on me, I'm pulling up on the Earth. So the two forces, one's on the Earth, one's on me, they're in opposite directions, it's the same magnitude, same type. So gravitational force down on me, up on the Earth. So the forces with respect to each other in the pair, forces with respect to, I'll just write with respect to pair, friction, they'll be beside each other in opposite directions. They're anti-parallel. Tension, the two forces in a tension pair will always be pointing towards each other. Normal force, the forces will always be pushing away from each other. Normal force is what keeps one object from going through another. I have a normal force acting on me from the ground. So the ground is pushing up on me. Likewise, I'm pushing down on the ground. And gravitational force, the two forces will always be towards each other. So tension and gravitational force are trying to pull objects towards each other. Normal force is trying to push things away from each other. And then forces with respect to the objects. Friction is parallel to surfaces of contact. And they oppose desired relative motion. Ethan, you need me to translate? You're squinting like you can't read my writing.
Parallel to surfaces of contact?
Yes.
Okay.
A chain, it's always along the line, or tension along the line of the taut rope, chain, string, whatever's causing it. Other is problem specific. Sorry, I skipped over other for forces with respect to the pair. Other is a case, when you're doing a force diagram, you would draw the forces in pairs, unless there's an other involved, in which case you only draw one of the two forces for a case of other. And hopefully, as we come to exceptions, you'll pick up on when you can and cannot. So a 3 Newton box is pushing to the right on or 3 Newton forces acting on a box to the right. Well, I know there's a force acting to the right on the box, so there's got to be a force acting left on something else, but I don't bother writing that.